So in this reference node embedding or reference point embedding technique, we somehow model the distance to different landmarks or different locations in the data. And PCA now goes a completely different way. We'll see that PCA and also singular value decomposition tries to come up with some kind of combination of the original features. So in the reference point embedding, the original features don't really visible somehow. I mean, of course they are in these new features because the distances to the reference points somehow depend on the original features, but they are not really capable. So we don't really see the original features. Now in PCA it's a little bit different because PCA tries to come up with actually a linear combination of the original features, and we'll see first of all in a kind of intuition or kind of motivation why that could be a good idea. So let's jump in and see what PCA is about. So first of all, as I said before, a short motivation. We want to compare the grades of students, or we want to compare students by their grades, and we only have the grades in physics and statistics, and we want to say, okay, those are the good or probably the best students, and those are the not so good students, probably the worst students. And if we have a look at, so maybe this is our data set here with all the students. So the students are plotted according to their grades in physics and in statistics. And the question is, if we want to compare among those students, which grade should be more should be used to compare about, which are more discriminative, statistics or physics? Well, if you have a closer look at the scale here, we see that the variance in statistics is very small, so it's not really significant to say those guys here are the best ones and those are the worst ones, because they are so similar, the grades are so similar. It probably doesn't make sense to do that. But in physics, the picture is completely different. We have a kind of a spread here between 20 and more than 80, probably 90. So it probably makes much more sense here in physics if we just look at the physics feature, just at the physics grade, to say, okay, those are the good ones, the good students, the best students, and those are probably the worst students. So the answer to the question is, which grade should be used to compare among the students? It's probably physics, because the variation along this axis is much larger, so it's much more significant if someone is up here or down here, rather than if we look at statistics, where we just have the best students are somewhere shortly above 50, and the worst students are shortly below 50. That's not really significant. So variation or the spread of the points of the observations along a feature may be a good indication of how good this feature is in order to compare among observations, and going one step further, maybe also in order to find patterns in that data. So we look for directions of high variance, of high variation, of high spread, of high variation. Now, suppose that the plot looks a little bit different, so the grades are a little bit different, like here. So there's a kind of linear positive correlation. So if you are bad in statistics, you're also bad in physics. If you're good in statistics, you're also good in physics. So probably that is what is much more realistic in real cases, in the real data. So the plot looks like this one here. What is now the best way to compare the students? Well, we have two features which have more or less the same grade. Okay, we could use both of them, of course, one of them, but they are somehow redundant. So maybe, and considering the ideas from here, from above, it's even better than just looking at statistics or just looking at physics. We could even try to look at this specific direction here, which is a linear combination of statistics and physics. Because along this line here, the gray line here, the gray direction here, we have the highest spread. We have the highest variance, even higher than just statistics and just physics. So in that case, we should take a linear combination of the two grades, which actually represents this direction of highest variance to get the best results, to get the best comparison. You know? And that's the case for, obviously, for correlated data. Yeah. So, and since we are interested in correlated data, redundant data, and also correlated data is very common in real-world applications, we probably have to look for these linear combinations rather than just for those individual features that have a high variance. Yeah? But the idea basically is the same. We look for the directions of highest variance, because in these directions the spread is highest, okay, and that means that the comparison among worst and best, for example, are most significant. Yeah? And once again, if we compare observations, the next step is to search for patterns among those observations. So maybe the same idea, looking for directions of highest variance, is also good for looking for patterns. Yeah? So that's the basic idea of PCA. Yeah? So PCA, what PCA does actually, just a spoiler because we will have a look at the details, of course, later on. So PCA returns, in that case, for the two-dimensional data set, which we have here, statistics and physics, we have two features. It's a two-dimensional data set. PCA would return two principal components. The first principal component gives the direction of the maximum spread in the data, which is this one here. Well, have a look at the first one. So this is the first principal axis with the maximum spread. Yeah? And the remaining principal components are orthogonal to each other, to the first one. So well, there can be only one further, which is orthogonal, which is this one here. So that is the second principal component. So in general, PCA returns for a d-dimensional data set d principal components, which are orthogonal to each other. And the first one gives the direction of the maximum spread of the data. The second gives the direction of the maximum spread of the remaining data, perpendicular, orthogonal to the first. Yeah? And that would be the green one here. So this one, the red one here, would be the first principal component, the first principal axis with the highest spread. And the green one would be the second one. In that case, that's it, because the original data set is two-dimensional. Yeah, but before we talk about how to actually get those principal components, how actually principal component analysis works, we have to talk about normalizing the data. Normalizing data has, we talked about it before, different reasons. Yeah. One is to get comparable features, comparable distances also then. So normalizing is always a good idea. And a very, very common way to normalize features is by subtracting the feature or the values of the features with the mean of the value of all the features. So we have a feature X, and we can compute the mean value of all values of all observations in that feature, which is X bar here. And we can subtract from all original features the mean of this feature and divide this value by the standard deviation, which is denoted here with Sx, the standard deviation of feature X. And that gives us the normalized feature values, X, what is that, snake here, or tilde. So that is original X minus mean times divided by standard deviation. Yeah? And that actually gives us a feature, or all the features in that case are then have the same mean, because the mean is then 0, obviously, and the standard deviation is normalized to 1 for all features if we do that with all features correspondingly. Yeah? And here is an example. If you consider the following data set with different body heights measured in different units, so we have different persons, different observations, and we measure for each observation the body height and record that in different units, centimeters, meters, and feet. Yeah, so you see here the corresponding values. Then you see here the mean and the standard deviation for the different features actually. So each object, each person has 3 features, the same feature in that case actually. but in different units, in different scales. So the means and the standard deviations are different. And if we normalize everything, so if we normalize this feature by subtracting the things here by the mean and dividing by the standard deviation, the same doing with here. So subtracting everything with mean divided by the standard deviation, and so on and so on. If we do that, we get a normalized body height for all these three features actually, and so for all these three features we get the same measures. Yeah, so you can just compute that with your Taschenrechner or whatever. So you get the normalized things, and the mean here now will be 0, and the standard deviation of all these three values will be 1. Yeah. So that is the usual way statisticians do the normalization, and I can just recommend to do that actually. Yeah. So why should you do that? Well, it puts features into comparable units. We just talked about that. So we make sure that all normalized features have a mean and a standard deviation of 1. That avoids numerical instabilities in several algorithms. So for example, if a feature has very low or very high values, but nothing in between somehow, then this may cause numerical instabilities in machine learning algorithms and stuff like that. Yeah? And as I told you before, it also helps computing meaningful distances between the observations. And finally, and that is basically what we are now targeting, if we want to find directions of highest variance, it might be better to do that on normalized data, because otherwise things that have a large scale, like centimeter in that case, would somehow dominate the others here. So the spread here in this first feature may dominate the spread and the variation in the other features. Yeah, and that might be not so good if we are to find directions of highest variance, even though they are somehow linear combinations of original features, but still unnormalized features may introduce biases or stuff like that. Yeah? So we use typically normalized data for doing PCA.